Hi, we're continuing on proteins, and we're specifically talking about in this section of Chem 138, Chapter 16, the function of proteins called enzymes. Enzymes are biological catalysts, and a catalyst means two things. It has a two-part definition, and that is that it lowers the amount of energy that it takes to activate the reaction, and it also regenerates itself. Enzymes typically work by fitting two of the substrates into an active site of some sort and causing the two reactants to come together in exactly the right angle and proportion and things like that. And then once that reaction goes forward, it releases the product, and then you have your enzyme catalyst regenerated again to do the next reaction. Okay, so you may see an energy diagram that talks about catalysts on the final exam. You already had an energy diagram on the midterm, so this will relate to that. So make sure that you go back and review those energy diagrams. When you have an enzyme, typically it will end with the ASE ending. For instance, an enzyme that is able to catalyze the reaction of sucrose is called sucrase. One that causes oxidation in oxidative reactions in the body is called an oxidase. And a common, so our common names that don't end in ASE that you'd have to become familiar with actually to know what the names were. There's not a sort of rhyme or reason. It's named sort of randomly in the sense that each one takes on an individual name. It's not like IUPAC naming system. So a common name for a digestive enzyme is pepsin or even trypsin. Okay. There's several classes of enzymes, including oxireductases that are involved with either the oxidation or the reduction of a reaction. Transferases cause the transfer of groups of atoms from one molecule to another molecule. There's also hydrolases that are involved with hydrolysis. We learned about hydrolysis with the esters in, gosh, what chapter was that? In Chapter 15, actually, with the lipids. If you were to hydrolyze an ester bond, you're breaking that ester bond, and those are the types of enzymes that are involved with that type of reaction. A lyase is able to remove double bonds or add atoms to remove double bonds. Isomerases rearrange atoms into different isomers. And ligases are able to use energy in order to perform synthetic reactions within the body. Okay, I do not expect you to have a question like this on the final exam. Okay, but there may be a question such as this on the homework. So I'm just going to flip through that because I'm kind of concentrate. And the answers are for A, you have an isomerase because it's converting from a cis to a trans. And B, it's going to remove hydrogen, so we call it a dehydrogenase. If we have something that combines molecules, we call it a synthetase. And if we add an amine, for instance, it's an aminase. I do not expect you to know all those names again for the final exam. If they're available in the book for the homework, that's different. It's just to get you familiar with some of the more common enzymes that might be present. Now, within an enzyme, there typically is an active site, and that active site is where the substrate or the reactants come together to meet, react, and then are finally released as products. Sorry, the room is a little messy today. I didn't realize some of this stuff. And so there's an active site, and oftentimes there's other sites where coenzymes or vitamins are able to interact with the enzyme as well. Okay, and so we find this active site, or what they call the binding site, of where the substrate will bind in. Once the substrate initially is in the active site, we call it the enzyme substrate binding process. And so if you were to write a reaction, a generalized reaction where we had just E representing the enzyme, S representing the substrates, and the complex being ES. So when we have a complex within the active site, we call it ES for the generalized chemical reaction. and then the substrate is then converted into product, and the enzyme releases the product, and you get the enzyme back. So you may have to do a generalized reaction, so pay attention to that. E plus S can produce, and it's a reversible reaction, ES complex, right? And then it will release E, which is your original enzyme, and P, your product that came from the substrates. Okay, and then once that enzyme is released, it can be used again and again. For many, many years, we thought there was only really a lock and key type of model that represented enzymes, and that's where in the active site, the substrates matched exactly the shape of the enzyme active site, and the substrate then locked in, so to speak, the key being sort of the substrate. But what we have found is that that typical lock-key method is not really usually the case. It's really usually an induced fit model where the enzyme active site is not as rigid as we thought previously, but rather a little more flexible, so that different types of substrates can sometimes fit into one type of enzyme. So enzymes can sometimes bind more than one type of substrate. And they can have a larger range of substrates that can fit into that active site. So pay attention to this model where you have the enzyme binding into the substrate, and remember that when the enzyme and the substrate complex to do the reaction, we call it the enzyme-substrate complex. Okay. This is just a further example of two substrates coming together within the sucrase. Okay, they complex together and then they're released, and you get your two products, okay? And it just happens over and over and over again. So diagnostic enzymes are enzymes that we look for in the body when certain conditions are taking place. We'll express more of that enzyme when there's those conditions taking place. For instance, the body will release some LDH, high levels of LDH, when there's a heart attack or liver disease present. And other types of diagnostic enzymes that we use to look at the levels of. I don't expect you to know these enzymes for the final exam. I do want you to take a look at them just because they have some interesting facts about what they look for when they go to the hospital. It's always good to have a little bit more power of knowledge when you're talking about your health. So you can go ahead and take a look at table 16.10. I don't remember if there's a couple of homework questions on it, but you can easily look those up. Isoenzymes are enzymes that have the ability to catalyze reactions isoenzymes are enzymes that have the ability to catalyze reactions, but the same type of reaction, but we find them in different types of tissue. So maybe you have lactate dehydrogenase, but you find it in heart muscle, but you also find it in skeletal muscle and the liver. And those enzymes could be slightly different, but perform the same type of reaction within different tissues. Okay, and these are just some examples. You can stop the tape if you'd like, but I'm going to move on. But you can take a look at some of the different ones if you find some interest in that. Again, these types of information, these very specific types of information, I'm not going to have you know. This is just an example of the levels of increase in some of the diagnostic enzymes, and it's just showing you some things that people see when, or what doctors see in the levels of LDH when there's been a heart attack that takes place. So if they monitor you for a couple of days, they're able to see, okay, yes, he has elevated levels of LDH, therefore we need to consider that a heart attack or whatever. So anyway, you're a little bit more educated on that subject. What do you need to know for the final exam when it comes to enzymes? You'll have to know the non-specific information. I mean, I don't expect you to know these specific types of enzymes. I expect you to understand that when you see a protein that's listed as an ASE ending, that you should recognize that's probably an enzyme that they're talking about. Also, I would like you to understand that temperature and pH have something to do with the action of the enzymes. there's a particular or optimal temperature that we'll find that the enzyme actually functions at. And if it's not at that temperature, the enzyme will not function properly. So be able to reproduce one of these charts that compares the reaction rate to the temperature. And you can just see that the optimal temperature is at about 38 here, where you have the maximum enzyme activity, okay? And if you get too high above in temperature, you can actually cause denaturation, which we're going to talk about in just a moment. So the other influence on enzyme action is your pH, so the amount of acidity or basicity that you have present. So all the enzymes will be slightly different, but somewhere around 7.2 is typical for an enzyme to be most active. So be able to, again, reproduce one of these reaction rates versus pH charts on your final exam. So this is just table 16.11 is telling you sort of the optimum pHs that you'll find. Notice that they change a little according to whatever the type of enzyme is, that we have very low pH for something that is a digestive enzyme like pepsin, and we have high pHs for enzymes that work in the liver at 9.7. So there's a distinct difference in the pH optimal activity depending on what type of enzyme you might be talking about. Furthermore, we have to keep in mind that the amount of substrate concentration does have an effect on the ability or the activity of the enzyme itself. If you supersaturate the enzymes that are present and you're putting a bunch of substrate in, there's going to be a level where everything, all the active sites are complexed with the substrate, and there's no more active sites to be able to bind into until those are released. And so we be able to recognize these charts that compare the amount of enzyme concentration to the amount of substrate concentration. Okay, so how can we stop an enzyme from catalyzing a reaction? If we'd like to do that artificially, we could put in an inhibitor, or even the body naturally will put inhibitors sometimes in that compete with the substrate. In that case, if you have an inhibitor, it will be a molecule that is similar in structure to the substrate that binds into the active site in complexes. You can have reversible ones that are then released and really don't cause a reaction to happen at all. You can also have inhibitors that can bind in permanently and cause that enzyme to be sort of deactivated. And those are really serious types of competitive inhibitors. So you can have both reversible and non-reversible inhibition. Okay. A non-competitive inhibitor is something that is able to distort the shape of the enzyme so that the active site is not available. Okay, so we have both competitive that fits into the binding site or the active site, and we have non-competitive inhibitors also that can prevent binding by sort of binding onto another site within the molecule, not necessarily the active site. It causes the enzyme not to be able to fit around the substrate properly, and then it inhibits the reaction. Irreversible inhibition, as I mentioned before, is where you have something bind in and it's not able to let go. Usually this is due to the fact that it's covalently bonded into the active site or even into another portion of the molecule that doesn't allow the enzyme to shape correctly. So be aware that there's both reversible and irreversible. Nerve gas, for instance, or some of the insecticides, or even some antibiotics are able to bind into active sites or other places within the enzyme and cause it not to be able to function. So inhibition causes enzymes not to function, but overall we can get most proteins not to function by performing denaturation. Denaturation can be accomplished by a series of ways. You can add heat and it will break some of the hydrogen bonds within it, and it causes the protein structure to go from a tertiary or quaternary structure to secondary or even primary structure. When you do that, you've denatured the protein. Okay. You can also put it in the presence of non-optimal pH solvents or solutions, and those will cause the H bonds again to break up, and it disrupts the ionic bonds as well, and so it causes the protein chain to dismantle. It stays within its primary structure but doesn't have that secondary, tertiary, or quaternary structure. Also, if you bind in heavy metals, that's why lead and other types of metals are so dangerous, because once those get coordinate into the protein, they can cause the protein to distort and then permanently distort, so it's non-functional. And that's why you can get poisoning from heavy metals. They often react with the disulfide bonds within the protein and form solids or aggregate, and so they cause that type of poisoning. And it's non-reversible, so it can be very dangerous. Of course, agitation, if you think of an egg as protein, you think of whipping the egg before you cook a scrambled egg. That also is a way that we denature proteins and cause them to be inactive. In general, you can cause denaturation where it's a gentle type of denaturation where you get the primary structure all out in one strand, and you can renature it by gently using pH or temperature in an optimal way to get it to renature again. However, oftentimes if you're using heat, metals, or agitation, you're not able to get those proteins back to a normal type of protein again. So table 16.7 identifies the different types of denaturations that can take place, and you can check that out and utilize that for some of the homework questions. I do want you to be aware of all of these types of denaturations also for the final exam. As I said before, there are also sites within an enzyme that help the reaction to go forward. We call these types of molecules that can bind into different parts of the enzyme to cause it to become functional coenzymes. Okay, and those just they assist with the catalytic activity. They can either be coenzymes or what we call cofactors of the enzymatic reaction. Here's just some examples of some metal ions that are used as cofactors, including copper, iron, zinc, magnesium, manganese, and nickel. And so if you happen to be low on those types of minerals, then your enzymatic reactions may not be working properly. So it's always important to pay attention to your nutrition, make sure that you're getting all of the minerals and vitamins that you need. There's both water-soluble vitamins that help with cofactoring the enzymatic reactions, including citric or ascorbic acid, which we call vitamin C. These types of water-soluble vitamins that are listed in table 16.13, we're able to eat plenty of, and if we have extra of those types of vitamins, we're able to excrete them out. And you can take a look at the table 16.13 to see what all the different vitamins are related to, what type of enzymatic reactions they're related to. I will not hold you responsible for understanding that thiamine is involved with decarboxylation, but I will hold you responsible for understanding that water-soluble vitamins, fat-soluble vitamins, and minerals are responsible for helping with the enzymatic action. Water-soluble vitamins are able to be excreted if there's excess water-soluble vitamins present. One of those water solubles include vitamin C, okay, and that's probably one of the big stars of the vitamins, of the water soluble vitamins. But also pay attention to the fact that all of the B vitamins are considered water soluble. You've got biotin and folic acid that are also water soluble vitamins. There's also a class of vitamins, including vitamin A, D, E, and K, that are called fat soluble vitamins, and that means that they're soluble in lipid environments, but not aqueous environments, okay? So they're able to interdisperse themselves amongst lipids, but not amongst aqueous environments. And therefore, if you have excess of fat-soluble vitamins, they can become toxic because we're not able to excrete them out through our regular aqueous excretion system that we have in our body. So it's important that you don't take too much of the fat-soluble vitamins, although you need them. They're important for vision with vitamin K. You've got some of vitamin D is involved with all kinds of things with the skin, and A and E as well. So they're also important with bone formation with vitamin D, antioxidants, and blood clotting. So they're important to be there. However, when you take those vitamins, they're stored in the body until further use. And if you have excess of those, then you can literally overdose on those fat-soluble vitamins. So they can be very, very dangerous. So later on in table 16.3, it lists the fat-soluble vitamins. You can look and see what they're involved with. What do you need to know about fat-soluble vitamins? You need to know which vitamins those are, because those can be dangerous if you don't understand what they are. So I expect for the final exam that you know which fat-soluble vitamins there are, and that's just A, D, E, K, A, DEC. Okay, so remember those. And I also want you to remember that too much of the vitamins will cause an overdose, so they can be dangerous. Vitamin A we find in a lot of the orange pigmented vegetables, and also in broccoli. I'm not going to go over the different types of fat-soluble vitamins. I just want you to know the information that I just mentioned. I unfortunately have a sort of a emergency to go to, so check out the concept map on amino acids, proteins, and enzymes, and make sure that you understand everything. If you don't, go ahead and send me an email that you need some more description about whatever it is that you need information about, and I will get back to you on that. So that was the second half of the protein chapter. We have one more chapter left, and that's DNA, and we'll talk about DNA and protein relationship in the next video. Thanks so much, guys, and have a great day.